Hello everyone and welcome back. If you're building apps with Flutter and you think your app is secure, it's probably not as secure as you think. More than 70% of mobile apps fail basic security tests. Flutter apps are not an exception. In this video, I will show you exactly how Flutter apps get hacked, the security mistakes even experienced developers make, and how to fix them before real damage happens. This is not a theory. Everything in this video is based on real attack techniques, the OWASP Mobile Top 10, and production Flutter apps used by real users. So if you care about user data, money, or your reputation as a developer, watch this video until the end, because one mistake here can break everything. Why Flutter security matters more than you think. Flutter makes cross-platform development fast and productive, but that convenience often creates a false sense of security. Many developers assume that because Flutter is backed by Google and compiles to native code, their applications are inherently secure. In reality, Flutter does not eliminate security risks, it simply changes where those risks appear. A Flutter application ultimately runs on platforms like Android and iOS, each with its own security model, permission system, storage mechanisms, and vulnerabilities. Flutter acts as a layer on top of these platforms, but it does not automatically secure how data is stored, how network communication is handled, or how authentication and authorization are implemented. Those decisions are still entirely in the developer's hands. Mobile applications also run in environments that developers do not control. Once an app is installed on a user's device, attackers can analyze the compiled binary, intercept network traffic, manipulate runtime behavior, and attempt to reverse engineer the app. Rooted and jailbroken devices make these attacks even easier. This means that trusting the client, whether for authentication, authorization, or business logic, is inherently dangerous. What makes Flutter security particularly tricky is that many vulnerabilities are invisible during development. The app functions correctly, the UI behaves as expected, and no obvious errors appear. Meanwhile, sensitive data may be stored insecurely, network requests may be exposed to interception, or secrets may be embedded directly in the application binary. These issues often remain unnoticed until real users are affected. A single insecure decision, such as storing tokens in plain text, skipping proper backend validation, or hard-coding API keys, can lead to data leaks, account takeovers, or financial loss. Security is not something that can be added at the end of a project. It must be considered at every layer, from architecture and data flow to deployment and monitoring. That is why Flutter security matters more than most developers realize. It is not about distrusting Flutter as a framework, but about understanding the shared responsibility between the framework, the platform, and the developer, and taking that responsibility seriously. What Flutter handles versus what you do. Flutter provides a powerful framework for building cross-platform applications, but it is important to understand its security boundaries. Flutter is primarily responsible for rendering the UI, managing widgets, handling state, and compiling Dart code into native binaries. While it offers some built-in protections, it does not take full responsibility for application security. Assuming that Flutter automatically secures your app can lead to serious vulnerabilities. What Flutter does handle well is memory safety at the language level. Dart avoids many common issues found in lower-level languages, such as buffer overflows and manual memory management errors. Flutter also benefits from platform-level sandboxing provided by Android and iOS, which helps isolate apps from each other. Additionally, Flutter supports code obfuscation during the build process, making reverse engineering more difficult, though not impossible. However, many critical security concerns are outside Flutter's scope. Flutter does not secure your API keys, authentication logic, or authorization rules. It does not enforce encrypted data storage, protect your network communication, or validate backend responses. If sensitive data is stored insecurely, if network requests are not properly protected, or if business logic is trusted on the client, Flutter will not stop those mistakes. Network security is another area where responsibility lies entirely with the developer. Flutter provides HTTP libraries, but it does not guarantee secure communication. Decisions such as enforcing HTTPS, implementing certificate pinning, handling tokens safely, and validating server responses must be implemented deliberately. Without these measures, Flutter apps are vulnerable to man-in-the-middle attacks and data interception. Flutter also does not protect against compromised devices. Rooted or jailbroken devices can bypass many platform-level protections, allowing attackers to inspect memory, modify app behavior, or spoof system responses. Detecting these conditions and deciding how the app should respond is the developer's responsibility, not Flutter's. In short, Flutter is a tool, not a security system. It provides a solid foundation and some helpful mechanisms, but real application security depends on how developers design data flow, trust boundaries, and platform interactions. Understanding what Flutter handles and what it does not is the first step toward building truly secure Flutter applications. OWASP Mobile Top 10 for Flutter developers. OWASP, the Open Web Application Security Project, is a global nonprofit organization dedicated to improving software security. It is best known for publishing the OWASP Top 10 lists, which identify the most critical security risks affecting applications. While many developers are familiar with the OWASP Top 10 for web applications, OWASP also maintains a separate Top 10 specifically for mobile applications, reflecting the unique threat landscape of mobile platforms. The OWASP Mobile Top 10 applies directly to Flutter because Flutter apps are still mobile applications at their core. Even though Flutter uses a single codebase and a modern framework, the final product runs as a native app on Android and iOS. This means Flutter apps inherit the same risks as any other mobile app, including insecure storage, unsafe network communication, weak authentication, and exposure to reverse engineering. Flutter does not exempt an app from these risks. It simply provides a different way to build it. One of the key differences between mobile and web security is the environment in which the application runs. Web applications primarily execute on servers controlled by the developer, with users interacting through browsers. Mobile applications, on the other hand, are installed directly on user devices that developers do not control. Attackers can analyze the app binary, intercept traffic, manipulate runtime behavior, and run the app on compromised devices. This makes client-side trust far more dangerous in mobile apps than in web applications. Another major difference is local data exposure. Mobile apps frequently store data on the device for performance and offline access, including authentication tokens, personal data, and cached responses. If this data is stored insecurely, attackers can extract it directly from the device. In contrast, web applications typically store sensitive data on the server, reducing the impact of client-side compromise. This is why insecure data storage is a top mobile risk, but less prominent in web-only threat models. Reverse engineering is also a much bigger concern in mobile security. Unlike web applications, where source code is largely hidden on the server, mobile apps distribute their compiled binaries to every user. Attackers can decompile or analyze these binaries to understand application logic, locate secrets, and bypass protections. This is why obfuscation, tamper detection, and runtime protection are emphasized in the OWASP Mobile Top 10. The OWASP Mobile Top 10 is not a Flutter-specific list, but it maps extremely well to Flutter development practices. Issues such as improper platform usage, insecure communication, weak cryptography, and poor authorization logic often appear in Flutter apps due to misunderstandings about platform APIs, reliance on client-side logic, or misuse of third-party packages. Understanding these risks helps Flutter developers make better architectural and security decisions early in the development process. Ultimately, OWASP is not a checklist to blindly follow, but a framework for thinking about risk. For Flutter developers, the Mobile Top 10 serves as a practical guide to understanding how real attackers think, where apps commonly fail, and which mistakes have the highest impact. Using OWASP as a reference allows developers to prioritize security work effectively and build Flutter apps that are resilient in real-world conditions. M1. Improper platform usage. Improper platform usage is the first risk in the OWASP Mobile Top 10, and it is especially relevant for Flutter developers. This category covers situations where an app misuses, misunderstands, or ignores the security features provided by the underlying platform. Even though Flutter abstracts away much of Android and iOS development, the app still relies heavily on platform APIs, permissions, and system services. A common mistake is assuming that Flutter automatically enforces correct platform behavior. In reality, Flutter simply exposes platform capabilities through plugins and channels. If a developer requests excessive permissions, uses platform features incorrectly, or ignores platform security guidelines, the app becomes vulnerable. Examples include requesting permissions that are not strictly necessary, misusing biometric APIs, or incorrectly handling secure storage mechanisms like Android Key Store or iOS Keychain. Permission handling is one of the most frequent sources of improper platform usage. Requesting too many permissions increases the attack surface and raises user suspicion, while requesting permissions at the wrong time can lead to unintended access patterns. In Flutter apps, this often happens when developers rely on third-party packages without fully understanding what permissions those packages require or how they behave on different platforms. Another common issue is incorrect handling of sensitive platform features. This includes misusing biometric authentication, failing to secure background snapshots, or allowing sensitive data to appear in screenshots and app switcher previews. These are not Flutter bugs, but platform-level responsibilities that Flutter developers must explicitly address, especially when working with sensitive data such as financial or personal information. Improper platform usage also occurs when developers do not follow platform-specific security best practices. Android and iOS regularly update their security models, deprecate unsafe APIs, and introduce new protection mechanisms. If a Flutter app does not keep up with these changes, by using outdated plugins, old SDK versions, or deprecated APIs, it can expose users to known vulnerabilities. To mitigate this risk, Flutter developers must stay informed about platform security guidelines and treat Flutter as a bridge, not a shield. This means using well-maintained plugins, reviewing platform-specific documentation, requesting only necessary permissions, and explicitly securing sensitive platform interactions. Proper platform usage is about respecting the security model of each operating system and ensuring that Flutter integrates with it correctly, not bypassing it for convenience. M2. Insecure data storage. Insecure data storage is one of the most common and most dangerous security issues in mobile applications, including apps built with Flutter. This risk occurs when sensitive information is stored on the device in a way that allows attackers to access it easily. Because mobile apps often store data locally for performance and offline support, mistakes in this area can have serious consequences. A common misconception among Flutter developers is that local storage mechanisms are safe by default. Tools such as shared preferences, local files, or simple key-value stores are often used without encryption. When sensitive data like authentication tokens, session identifiers, personal information, or financial data is stored this way, anyone with access to the device, or with the ability to analyze the app's data directory, can extract it. Flutter apps are particularly susceptible to this issue when developers treat local storage as a cache rather than a potential attack surface. Even if data is meant to be temporary, it can still be exposed through backups, debugging tools, rooted or jailbroken devices, or malicious applications running on the same device. Attackers do not need to break your backend if they can simply steal credentials directly from the device. Another source of insecure data storage is improper handling of background state and snapshots. When an app is sent to the background, the operating system may capture a snapshot for the app switcher. If sensitive data is visible at that moment, it can be leaked through screenshots, screen recordings, or system-level previews. This risk is often overlooked in Flutter apps that display private information on screen. To mitigate insecure data storage, Flutter developers must be deliberate about what data is stored locally and how it is protected. Sensitive information should be encrypted using platform-backed secure storage mechanisms rather than plain-text files or preferences. Developers should also minimize the amount of sensitive data stored on the device and clear it when it is no longer needed. Ultimately, insecure data storage is not a framework problem, it is a design problem. Flutter provides the flexibility to store data in many ways, but it is up to the developer to choose secure options and understand the risks. Treating the device as an untrusted environment and assuming that local data can be accessed by attackers is the safest mindset when building secure Flutter applications. Flutter secure storage versus encrypted databases. Secure local storage is a critical part of mobile application security because mobile apps frequently store data on the user's device. In Flutter, developers typically choose between native secure storage mechanisms and encrypted local databases. While both approaches provide protection, they serve different purposes and are not interchangeable. Native secure storage relies on platform-provided security features such as Android Key Store and iOS Keychain. In Flutter, this approach is commonly used to store small pieces of highly sensitive data, including authentication tokens, session identifiers, and cryptographic keys. These systems are designed to protect secrets even if the device is compromised to some extent, and they often integrate with hardware-backed security when available. Secure storage is best used when the data is small, highly sensitive, and essential for authentication or encryption. It is not designed for large datasets or frequent read-and-write operations. Storing large amounts of data in secure storage can lead to performance issues and increased complexity. Its strength lies in protecting secrets, not managing application data at scale. Encrypted local databases, on the other hand, are designed to store larger volumes of structured data securely. Tools like encrypted key-value stores or encrypted databases allow Flutter apps to persist user data while protecting it at rest. These solutions typically use strong encryption algorithms and are optimized for performance and offline access. Encrypted databases are ideal for scenarios where the app needs to store user-generated content, cached API responses, or offline data that may include sensitive information. While this data is protected, it is still ultimately accessible to the app itself, which means encryption keys must be managed carefully. If keys are hard-coded or poorly protected, encryption becomes ineffective. The key difference between these approaches is intent. Native secure storage protects secrets that should never be exposed, while encrypted databases protect data that must exist on the device but should not be readable outside the app. In many secure Flutter apps, both approaches are used together. Secure storage holds keys and tokens, while encrypted databases store larger datasets using those keys. Choosing the correct storage strategy requires understanding the sensitivity, size, and life cycle of the data. Storing everything in secure storage is impractical, and storing secrets in a database is dangerous. Secure Flutter applications use each tool for its intended purpose, balancing security, performance, and usability. Protecting background screenshots and app switcher leaks. When a mobile app goes into the background, the operating system often captures a snapshot of the current screen to display in the app switcher. If sensitive information is visible at that moment, such as personal data, account balances, messages, or authentication details, it can be exposed unintentionally. In Flutter apps, this behavior is easy to overlook because the app continues to function correctly, even though private data may be visible outside the app's active context. This risk becomes more serious on shared devices, compromised devices, or when screen recording and screenshots are enabled. Attackers or unauthorized users do not need to break encryption or intercept network traffic to exploit this issue. They can simply view the app preview in the system task switcher or retrieve cached screenshots stored by the operating system. For apps that handle financial, medical, or personal data, this kind of exposure can be just as damaging as a traditional data leak. Preventing background screenshot leaks requires explicit action from the developer. Flutter apps that display sensitive information should obscure or hide content when the app moves to the background, rather than relying on default behavior. This typically involves detecting app lifecycle changes and temporarily masking the UI until the app becomes active again. Treating background snapshots as part of the attack surface helps ensure that sensitive data is protected not only during active use, but also when the app is paused or backgrounded. M3. Insecure communication. Insecure communication refers to how an application sends and receives data over the network without sufficient protection. For Flutter apps, this risk is critical because nearly every modern app communicates with a backend for authentication, data synchronization, analytics, or payments. If this communication is not properly secured, attackers can intercept, read, or even modify the data in transit. A common mistake is assuming that using HTTPS alone is enough. While HTTPS is essential, it is not a complete solution. Misconfigured SSL, accepting invalid certificates, or disabling certificate validation during development can open the door to man-in-the-middle attacks. These attacks allow an attacker on the same network, such as a public Wi-Fi hotspot, to intercept sensitive information like login credentials, tokens, or personal data. Flutter apps are particularly vulnerable to insecure communication when developers prioritize convenience over security. Examples include allowing clear text traffic, trusting all certificates, or failing to validate server responses properly. These shortcuts may make development easier, but they significantly weaken the app's security posture in production. Another issue is the transmission of sensitive data without proper safeguards. Sending passwords, tokens, or personal information without encryption or over insecure channels exposes users to serious risks. Even when encryption is used, weak configurations or outdated protocols can undermine its effectiveness. In mobile environments, attackers often exploit these weaknesses using network monitoring tools or proxy setups. To mitigate insecure communication, Flutter developers must treat the network as an untrusted environment. All communication should be encrypted, certificate validation should be strict, and additional protections such as certificate pinning should be considered for high-risk applications. It is also important to ensure that backend APIs enforce strong security rules, as mobile apps should never be the sole authority for validating requests. Insecure communication is not just a technical flaw, it is a trust issue. Users trust mobile apps with their data, often over unknown networks and devices. Failing to secure network communication breaks that trust and can lead to data breaches, legal consequences, and loss of user confidence. For Flutter developers, understanding and addressing this risk is essential to building secure, production-ready applications. Certificate pinning in Flutter. Certificate pinning is a security technique used to ensure that a mobile app only communicates with a trusted server by verifying a specific certificate or public key during a network connection. Instead of relying solely on the system's list of trusted certificate authorities, the app pins an expected certificate or key and rejects connections that do not match it. In Flutter apps, certificate pinning helps protect against man-in-the-middle attacks, especially on untrusted networks such as public Wi-Fi. While certificate pinning can significantly improve security, it is easy to implement incorrectly. A common mistake is pinning the entire certificate instead of the public key, which can cause the app to break when certificates are renewed or rotated. Another frequent error is disabling certificate validation during development and forgetting to re-enable it for production. Improper error handling is also a risk. Some apps silently fall back to insecure connections when pinning fails, which defeats the entire purpose of the protection. Certificate pinning should be used selectively, not universally. It is most appropriate for high-risk applications such as banking, healthcare, or apps that handle highly sensitive data. For general-purpose apps, aggressive pinning can introduce operational risks, including app outages if backend certificates change unexpectedly. When used, pinning should be combined with strong backend security, proper certificate rotation strategies, and monitoring. Done right, certificate pinning increases the cost of network attacks without sacrificing app reliability. M4. Insecure authentication. Insecure authentication occurs when an application fails to properly verify the identity of a user. In Flutter apps, this risk often appears when developers rely too heavily on client-side logic or treat authentication tokens as inherently trustworthy. While Flutter handles UI and interactions smoothly, it does not enforce secure authentication flows. Those decisions are entirely up to the developer. A common mistake is storing authentication credentials or tokens insecurely on the device. If tokens are saved in plain text or easily accessible storage, attackers who gain access to the device can reuse them to impersonate users. Another frequent issue is assuming that once a user is authenticated, their identity does not need to be revalidated. Expired tokens, replay attacks, and stolen credentials are all real threats in mobile environments. Some Flutter apps also rely too much on local authentication mechanisms without proper server-side validation. Biometric authentication, PINs, or device-level checks can improve user experience, but they should never replace backend verification. If authentication decisions are made only on the client, attackers can bypass them by modifying the app or manipulating runtime behavior. To mitigate insecure authentication, Flutter apps must rely on strong, server-validated authentication mechanisms. Tokens should be short-lived, securely stored, and regularly refreshed. Sensitive authentication decisions must always be confirmed by a trusted backend, not by client-side logic. Authentication is about proving identity, and in mobile apps, that proof must be continuously verified. M5. Insecure authorization and role validation. Authorization is about determining what an authenticated user is allowed to do. Even when authentication is implemented correctly, authorization failures can completely undermine application security. In Flutter Apps, insecure authorization often happens when developers trust the client to enforce roles, permissions, or access controls. A common authorization flaw is relying on UI-level restrictions. Hiding buttons, disabling features, or showing different screens based on user roles does not provide real security. Attackers can bypass these controls by manipulating network requests or modifying the app. If the backend does not validate permissions, users can access functionality they were never meant to use. Another frequent issue is failing to validate roles and permissions on every request. Mobile apps are easy to reverse engineer, and attackers can replay or modify API calls to escalate privileges. If the server assumes that the client has already enforced authorization, it creates a critical vulnerability that can lead to data exposure, account takeover, or administrative access. In Flutter development, this risk is often amplified by shared codebases and rapid development cycles. Developers may reuse API calls across multiple user roles without implementing proper checks, assuming that the app flow will prevent misuse. In reality, attackers do not follow the intended app flow. Mitigating insecure authorization requires a strict server-side approach. Every sensitive operation must be validated by the backend, including role checks and permission enforcement. The client should be treated as untrusted at all times. Authorization is not about what the app allows the user to see. It is about what the system allows the user to do, and that decision must never be left to the Flutter app alone. M6. Broken cryptography. Broken cryptography refers to the use of weak, outdated, or incorrectly implemented cryptographic techniques. In Flutter apps, this risk often appears not because developers intend to do something insecure, but because cryptography is easy to misuse and hard to get right. Simply using encryption does not automatically make an app secure. A common mistake is relying on deprecated or weak algorithms, such as MD5 or SHA-1 for hashing sensitive data. These algorithms are no longer considered secure and can be broken using modern computing power. Another frequent issue is implementing custom cryptographic logic without fully understanding key management, randomness, or algorithm guarantees. Even small mistakes, such as hard-coding encryption keys or reusing initialization vectors, can completely undermine encryption. Flutter makes cryptographic libraries easily accessible, which is both a strength and a risk. Developers may encrypt data, but then store the encryption key directly in the app binary, making it trivial for attackers to extract. In these cases, encryption provides only the illusion of security. If an attacker can reverse engineer the app and retrieve the key, the encrypted data offers no real protection. To mitigate broken cryptography, Flutter developers should rely on well-established, industry-approved algorithms and libraries, and avoid inventing their own solutions. Encryption keys should never be hard-coded or stored insecurely, and sensitive cryptographic operations should be designed with the assumption that the client environment can be inspected. Cryptography should be used carefully, consistently, and only when it actually improves security. Securing API keys in Flutter. Hard-coding API keys directly into a Flutter application is one of the most common and dangerous security mistakes. Because mobile apps are distributed as binaries, any secret embedded in the code can eventually be extracted through reverse engineering or static analysis. Even if the source code is private, the compiled app is available to anyone who installs it, which makes hard-coded API keys effectively public over time. A more secure approach is to manage secrets outside the source code using environment variables or build time configuration. In Flutter projects, this usually means defining secrets in files or build settings that are excluded from version control and injected during the build process. This reduces the risk of accidental exposure through repositories and makes it easier to rotate or revoke keys without changing application logic. For larger teams or production systems, secrets should be managed using dedicated secret management tools rather than developer machines. Obfuscation is often misunderstood as a solution for protecting secrets, but it is not sufficient on its own. While obfuscation makes reverse engineering more difficult, it does not prevent attackers from discovering embedded values at runtime or through memory inspection. If an API key exists in the client app, it should be assumed to be discoverable. The safest design is to limit what client-side keys can do and move sensitive operations to a trusted backend. Securing API keys in Flutter is about reducing exposure and designing systems that remain secure even if the client is fully inspected. M7. Poor client code quality and security bugs. Poor client code quality is a significant security risk because many vulnerabilities originate from simple coding mistakes rather than advanced attacks. In Flutter apps, these issues often appear as insecure API usage, improper error handling, excessive logging, or unsafe assumptions about user input and app state. A common problem is trusting data that comes from the client itself. Flutter apps frequently perform validation on the client for convenience, but client-side validation is easy to bypass. Attackers can manipulate inputs, modify network requests, or change app behavior at runtime. If the backend relies on the client to enforce rules, security failures are inevitable. Another issue is the careless use of third-party packages. Flutter's ecosystem is rich, but not all packages are well-maintained or secure. Using outdated dependencies, unreviewed code, or packages with excessive permissions can introduce vulnerabilities into an otherwise well-written app. Poorly written plugins can expose sensitive data, misuse platform APIs, or weaken the app's security model. Debug code and verbose logging are also common sources of security bugs. Leaving detailed logs, test endpoints, or debug flags enabled in production can leak sensitive information or expose internal logic. These issues are rarely intentional, but attackers actively look for them because they are easy to exploit. Mitigating poor client code quality requires discipline and process. Flutter developers should follow secure coding practices, review third-party dependencies carefully, and remove unnecessary code before production. Automated analysis, regular code reviews, and a mindset of distrust toward the client environment all help reduce the risk. Security bugs are often small and subtle, but their impact can be severe if left unaddressed. M8. Code tampering. Code tampering refers to any attempt to modify a mobile application after it has been built and distributed. For Flutter apps, this is an important risk to understand because once an app is installed on a device, it is no longer under the developer's control. Attackers can alter app behavior, bypass restrictions, or manipulate logic at runtime. In mobile environments, tampering often happens on rooted or jailbroken devices. These environments allow attackers to attach debuggers, hook functions, modify memory, or change how the app behaves without altering the original source code. In Flutter apps, this can lead to bypassing authentication checks, disabling security logic, or spoofing system responses, such as in-app purchases or device integrity checks. A common misconception is that code tampering can be fully prevented. In reality, any code running on a user's device can be modified in some way. The goal is not absolute prevention, but detection and mitigation. Flutter apps that rely heavily on client-side logic for security decisions are especially vulnerable because tampering allows attackers to alter or skip those checks entirely. To reduce the impact of code tampering, Flutter developers must assume that the client environment is hostile. Critical decisions should always be validated by a backend service, not enforced solely in the app. Additional protections, such as integrity checks, runtime monitoring, and detection of compromised environments, can help identify tampering attempts and respond appropriately, even if they cannot stop them completely. Code tampering is ultimately about trust boundaries. If the app is trusted to enforce rules on its own, tampering breaks that trust. Secure Flutter apps are designed with the assumption that the app itself can be modified, and they limit the damage that modification can cause. Detecting rooted and jailbroken devices in Flutter. Detecting rooted or jailbroken devices in Flutter is an important security measure for apps that handle sensitive data, such as banking, payment, or enterprise applications. Rooted Android devices and jailbroken iOS devices bypass the standard security mechanisms of the operating system, allowing apps or malicious users to access system files, modify app behavior, or bypass restrictions. In Flutter, developers can use platform-specific plugins or write native code integration to check for signs of rooting or jailbreaking, such as the presence of superuser binaries, unusual system file access, or modified app signatures. These checks help ensure the app is running in a secure environment and can protect against data theft, fraud, or unauthorized modifications. Root and jailbreak detection isn't foolproof, as advanced users can hide these modifications or manipulate the checks. Therefore, these mechanisms are often combined with other security measures, such as runtime integrity checks, encrypted storage, obfuscation, and secure network communication. Flutter plugins like root check or jailbreak detection simplify this by providing cross-platform APIs, but developers should always be aware of false positives and device compatibility issues. Detection strategies can range from simple checks, like the presence of root apps or access to restricted directories, to more advanced heuristics, like checking system property inconsistencies or integrity of system binaries. Deciding when to block users based on root or jailbreak detection depends on the app's risk profile. For highly sensitive apps, such as mobile banking, trading platforms, or corporate apps with confidential data, blocking access may be justified to prevent security breaches. For less critical apps, developers might opt for warnings or limited functionality instead of outright blocking, balancing security with user experience. Ultimately, implementing root and jailbreak detection in Flutter should be part of a layered security strategy that mitigates risk while minimizing disruptions for legitimate users. M9. Reverse engineering Flutter apps. Reverse engineering is the process of analyzing an application to understand how it works internally. Unlike web applications, mobile apps distribute their compiled code directly to users. This makes reverse engineering a significant risk for Flutter apps, as attackers can inspect binaries, analyze metadata, and infer business logic. Flutter apps are compiled into native binaries, which provides some protection, but it does not make them immune to analysis. Attackers can extract strings, inspect network calls, identify encryption routines, and locate embedded secrets. Even without fully reconstructing the source code, this information can be enough to exploit vulnerabilities or bypass protections. One of the most serious risks of reverse engineering is the exposure of hard-coded secrets. API keys, encryption keys, and sensitive configuration values embedded in the app can often be discovered through static analysis. Once exposed, these secrets can be abused independently of the app, leading to backend compromise or financial loss. Reverse engineering also enables attackers to understand how security mechanisms work, making it easier to bypass them. Obfuscation can make this process more difficult, but it does not eliminate the risk. Flutter's obfuscation tools raise the cost of analysis, but they should be viewed as a delay mechanism rather than a complete defense. Mitigating reverse engineering requires a layered approach. Sensitive logic should be moved to the backend whenever possible, secrets should never be embedded in the app, and obfuscation should be used to increase the effort required for analysis. Flutter developers must accept that reverse engineering is inevitable and design their applications so that understanding the app does not equal breaking the system. Flutter code obfuscation, strengths and limitations. Flutter code obfuscation is a technique used to make the dark code of your Flutter app harder to read and reverse engineer. When you build a Flutter app in release mode with obfuscation enabled, the Dart compiler renames symbols, methods, and classes into meaningless identifiers, making it difficult for someone analyzing the app binary to understand its structure or logic. This is particularly useful for protecting intellectual property, proprietary algorithms, or sensitive business logic from casual reverse engineering. Obfuscation is easy to enable in Flutter using build flags like obfuscate and split debug info, which also help reduce the size of the app's debug symbols. However, it's important to understand what obfuscation does not protect. It doesn't prevent runtime attacks, such as memory inspection, dynamic code injection, or tampering with API calls. It also cannot stop determined attackers from decompiling your APK or IPA and analyzing the app's behavior at runtime. Obfuscation only increases the difficulty of static code analysis. It slows down reverse engineering, but does not make it impossible. Any secrets stored in the app, such as API keys or credentials, should still be secured using proper encryption, server-side validation, or secure storage mechanisms. Realistic expectations are essential when using Flutter obfuscation. While it raises the barrier for casual hackers and can deter automated attacks, it should be viewed as one layer in a broader security strategy rather than a foolproof solution. Developers should combine obfuscation with other techniques like secure API design, code signing, runtime integrity checks, and encryption to achieve meaningful protection. Essentially, obfuscation protects how your code looks, but it doesn't protect how it behaves, so sensitive operations should always assume that the attacker can observe or manipulate the app at runtime. M10 Extraneous Functionality. Extraneous functionality refers to hidden, unused, or unintended features that remain in an application after development and testing. These features are often introduced for debugging, testing, or internal use, but accidentally shipped to production. In Flutter Apps, extraneous functionality can create serious security vulnerabilities because it exposes capabilities that were never meant for end users. A common example is leaving debug code or test endpoints in the production build. Developers may add temporary shortcuts, feature flags, or internal screens to speed up development, assuming they will be removed later. If these elements are forgotten, attackers can discover them through reverse engineering or runtime analysis and use them to bypass normal app behavior or access restricted functionality. Another frequent issue is excessive logging or verbose error messages. Flutter apps sometimes log sensitive information such as API responses, user identifiers, or internal state for debugging purposes. When this information remains in production logs, it can be extracted by attackers or exposed through system-level debugging tools, revealing valuable insights about the app's internal workings or backend structure. Extraneous functionality can also appear in the form of disabled security controls. During testing, developers may temporarily turn off authentication checks, certificate validation, or multi-factor requirements to simplify development. If these changes are not fully reverted before release, the app may ship with critical protections missing, creating easy entry points for attackers. This risk is especially dangerous because it often goes unnoticed. The app appears to function normally, and users may never encounter the hidden functionality during regular use. Attackers, however, actively search for these weaknesses because they are typically easy to exploit and require little technical effort. Mitigating extraneous functionality requires strict discipline and release processes. Flutter developers should remove all test code, internal features, and debug logs before production. Build configurations should clearly separate development and release modes, and production builds should be reviewed with a security mindset. Every feature in a released Flutter app should exist intentionally, serve a clear purpose, and be protected by appropriate security controls. Runtime Application Self-Protection, RASP, in Flutter. Runtime Application Self-Protection, RASP, in Flutter, is a security approach where the app actively monitors and protects itself while it's running. Unlike traditional security measures that rely on external systems, RASP operates from within the application, detecting and responding to threats in real time. In Flutter, RASP can help identify attempts to tamper with the app, such as code injection, unauthorized modifications, or reverse engineering attempts. By integrating native platform checks through plugins or platform channels, Flutter apps can monitor their own runtime environment and trigger responses, like logging, alerting, or even blocking suspicious activity. Key capabilities of RASP in Flutter include detecting hooking frameworks, debugging sessions, emulators, and other abnormal conditions. Hooking frameworks like Frida or Exposed allow attackers to intercept and modify app behavior, while debuggers can reveal sensitive logic. Emulators are often used for automated testing or malicious analysis, and tampering can indicate that someone is trying to modify the app's code or bypass security controls. Flutter developers can implement checks for these conditions using both Dart and native APIs, for instance, detecting system properties, unexpected process states, or known debugging libraries, and respond appropriately without requiring server-side intervention. While RASP significantly strengthens runtime security, it has limitations. Sophisticated attackers can still bypass some runtime checks, and false positives can frustrate legitimate users. RASP is most effective when combined with other security measures like code obfuscation, secure API calls, encrypted storage, and root jailbreak detection. The realistic expectation is that RASP adds an active layer of defense, increasing the cost and complexity for attackers, but it cannot guarantee absolute protection. In Flutter, adopting RASP ensures that security is proactive rather than purely reactive, allowing apps to detect and respond to threats in real time. Building a complete Flutter security strategy. Building a complete Flutter security strategy means thinking about app security as a full lifecycle, not just a single feature. At its core, it involves 5 key steps: identify, detect, protect, respond, and recover. Identify is about understanding what your app's critical assets are: user data, sensitive business logic, APIs, and authentication mechanisms, and knowing where vulnerabilities might exist. This step sets the foundation for a focused security approach by highlighting what needs protection and the potential threats that could target your Flutter app. Detect and protect work hand in hand. Detection involves monitoring for abnormal behaviors at runtime, such as rooting, jailbreaking, tampering, hooking, debugging, or unusual API access. Protection includes preventive measures like code obfuscation, secure storage, SSL pinning, encryption, and runtime application self-protection, RASP. In Flutter, detection can leverage both dark code and native platform APIs, while protection ensures that sensitive logic, user credentials, and communications remain secure even if an attacker tries to interfere with the app. These layers reduce the risk of data leaks, fraud, and reverse engineering. The final steps: respond and recover. Focus on what happens when a threat is detected. Responding could mean alerting the server, logging suspicious activity, restricting functionality, or blocking access, depending on the severity of the threat. Recovery involves restoring the app or its environment after an incident, ensuring minimal disruption to legitimate users, and updating the security measures to prevent similar attacks in the future. Taken together, these 5 steps form a holistic Flutter security strategy, a proactive, layered approach that protects the app throughout its lifecycle, balances user experience with security, and prepares the system to handle incidents efficiently. Final thoughts: security is a process, not a feature. Security in Flutter or any platform is not a single feature you can implement once and forget. It's an ongoing process that spans the entire app lifecycle. Many developers make the mistake of thinking that enabling obfuscation, root detection, or SSL pinning is sufficient. While these measures improve security, relying on them alone creates a false sense of confidence. Threats evolve constantly. New vulnerabilities in Flutter packages, third-party libraries, and operating systems emerge, as do sophisticated attack techniques like dynamic code injection, hooking frameworks, or API exploits. Treating security as a process means continuously monitoring, updating, and testing your app to stay ahead of these evolving threats. A long-term security mindset involves layered defenses, proactive threat modeling, and regular audits. For Flutter apps, this includes maintaining up-to-date dependencies, implementing runtime protections, encrypting sensitive data, enforcing robust authentication, and monitoring for abnormal activity. Security processes should also cover code reviews, automated testing, penetration testing, and post-release monitoring. Teams should document security practices and establish clear procedures for responding to incidents, applying patches, and updating security configurations as new threats are discovered. This ensures that the app's defenses remain relevant and effective over time, even as the attack landscape shifts. Finally, avoid false confidence by acknowledging that no app is perfectly secure. Security is about risk reduction, not absolute prevention. Developers should focus on mitigating the most impactful risks and being prepared to respond quickly if a vulnerability is exploited. Combining preventative measures with detection and response strategies creates a resilient Flutter app that can adapt to new threats. Viewing security as a continuous process, rather than a checkbox item, empowers teams to protect user data, maintain trust, and sustainably manage the long-term safety of their applications. Thanks for sticking with us through this deep dive into Flutter security. In this video, we covered everything from the basics of why Flutter security matters to advanced topics like secure storage, certificate pinning, authentication, authorization, cryptography, and runtime protection. We also explored real-world risks such as reverse engineering, code tampering, and hidden backdoors, and provided actionable strategies to safeguard your Flutter apps. If you found this video helpful, make sure to like, comment, and subscribe for more Flutter tips and tutorials. Don't forget to hit the bell icon so you never miss an update.